The thermoacoustic Stirling engine uses only sound waves for its energy generation. As it is externally heated, any heat source can be used to operate it, and it has no moving mechanical parts. This makes the engine highly reliable and almost completely free from wear, and it is perfect for building yourself using a simple 3D printer. If you are interested in some basic information about how the thermoacoustic Stirling engine works and how it's built, check out my YouTube channel, My Engines. Here, in a comprehensive 3-part series and many more videos, I describe all the components in detail, including a link to download all the construction plans and 3D models. You might even be interested in being part of the development process. Any help is welcome on our Discord server, in the comments, and soon on our little forum website too. Over the past few weeks, many contributors have developed fantastic new approaches to manufacturing all components using a 3D printer. It now even seems possible to 3D print the heating unit yourself from ceramic at a relatively low cost, rather than ordering it from a 3D printing service made from metal or ceramic. Some engine developers here are also working on the complex theoretical thermoacoustic design and simulation. However, there are still difficulties with the power extraction unit. The thermoacoustic machine can operate as a heat pump without any mechanical components, and it is set to transform heat pump technology in the future. Unfortunately, however, it is impossible to convert acoustic energy into electrical energy without moving masses. The design of the electricity generation system is therefore of crucial importance for the quality and long-term reliability of the thermoacoustic engine. Apart from the bidirectional impulse turbine, I have so far used a conventional cylinder with a piston for the various types of energy conversion. The cast iron piston used so far builds up high compression and runs very smoothly and reliably. Unfortunately, it is also very heavy and requires a lot of energy to accelerate. Furthermore, as power outputs continue to increase, the vibration has now become so high that balancing is necessary. I have already implemented this using a balancing lever with a counter-running linear generator or oscillating rotary generators, which worked very well, but also caused a few problems. That is why I am now conducting various tests using different, much lighter pistons made from Eiger's Iglidur W300, ultra-high molecular weight PE, and 3D printed PET-G with piston rings. The UHMW PE pistons generate high friction with little compression. The printed PET-G piston with piston rings has the same issues, but I still see potential here for improvement through extensive testing with different piston rings and pressure springs. The W300 piston has very low friction and excellent compression. Thanks to its low mass, it oscillates at almost twice the frequency of the heavy cast iron piston. This means almost double the potential power output with much lower impedance. The W300 piston runs extremely well, but unfortunately only when all the external conditions are right. If the piston becomes too hot due to continuous high-speed operation and expands as a result, friction increases and performance drops. Although I tempered the W300 blank before finishing it, the diameter increases over the weeks, which is probably due to the changing temperature during the test runs and the humidity. I think these issues can be resolved though, and with a bit of development work, the piston made from W300, which is also available in a similar form as filament for 3D printing, is a good choice. Experiments with energy recovery using spring-mounted piston end stops have also resulted in a noticeable increase in performance, which I intend to investigate further. Another balancing idea involves two 90-degree rotated pistons running in opposite directions within the power extraction unit. Although this would double the effort required for 2 cylinders and pistons, but it would be an elegant solution. To avoid the problems and complexity of using pistons entirely, a membrane or diaphragm can be used instead. Extensive testing in this area looks very promising, as this solution offers good sealing properties combined with low weight and simple manufacturing. I have now ordered a roll of TPU filament and will be using it to carry out comprehensive tests on membranes, diaphragms, spring elements and piston ring seals. I have only just learned that PBBA is even better suited than TPU due to its superior elastic properties. Do you know of any even better options for manufacturing a membrane or a diaphragm? As you can see, development of the thermoacoustic engine is progressing well. As always, I'm really looking forward to your feedback, ideas and suggestions in the comments and on Discord. If you would like to support the videos and the project even further, you will find lots more exclusive content, 3D models, drawings and files in the members area and on Patreon. Thanks for watching.